All right, I think we can go ahead and get started. It's my pleasure to introduce our speaker today, Dave Pooley from Trinity University in San Antonio. Dave got his undergraduate and graduate degrees in both in physics at MIT. And then he went to Berkeley as a postdoc for several years.
Yeah, as a Chandra fellow.
Chandra fellow, right? And then had time in his career to spend a year at University of Wisconsin-Madison, my favorite thing to live anyway, Madison, and then joined the faculty at Trinity. I'm sorry, at Houston, which is slightly harder, for a few years before going to Trinity for the last 5 years. Trinity is a really nice university to visit. They have a great program, so you get invited to get a talk there.
Thank you.
Yeah, so Trinity, Dave is going to tell us about this very exciting new project called Lynx today.
Thanks. Thank you for that. And before I get to that, what Jen said is actually an excellent segue to something I wanted to say right up front is we would love to have any of you come to Trinity and talk to us about the cool things that you're doing. This is an open invitation for grad students, for postdocs, for faculty. Come share with us the awesome type of work that you're doing. Trinity is a undergraduate only in the physics department, so we like to expose our undergraduates to a wide breadth of possible choices of research and possible career paths. And so we really love for people to come and share just, your story and what you're working on, and to give our undergraduates a sense of the variety of cool things that are out there. So consider this an open invitation, but I will also be happy to follow up, and I'll send some information to Jen, and maybe she could forward it along about getting in touch about coming to Trinity to talk. Before I get started, I want to do a quick poll, just to show of hands. How many of you have analyzed Chandra data? A few. How many of you have been involved with a project that has used Chandra data? Okay, so a few more hands have gone up. And I think that is a great evidence of why I wanted to come, why the Lynx team wants to come out, wants to get into the community and talk about our idea for this observatory. X-ray observations have immense power to help us understand the cosmos. For the simple reason that much of the baryonic matter for most of cosmic time and the sites of the most active energy releases in the universe are observable primarily, sometimes exclusively, in X-rays. So an X-ray observatory with the power to match the capabilities that we're going to have in other wave bands is a necessary discovery engine to help further our understanding of the universe. We know that JWST, along with the large optical telescopes that are being built and planned right now, are going to greatly expand our science frontiers. And so this presents a great opportunity, but also a great challenge for us, because we've seen time and again how having the capabilities in other wave bands makes all of the data that's collected that much more valuable. So what I was going to do in telling you about Lynx, there's a lot to say. I certainly can't cover all of it. I'm going to tell you a little bit about the mission and the instruments that would be on it, that we have envisioned on it. I'm going to tell you a bit about the science capabilities that it has and what we have defined as the 3 main areas that drove our observatory requirements, and also tell you a little bit about some other types of science that could be done with an observatory of this class. So the Lynx X-ray Observatory is built upon proven architecture with a lot of heritage that we have in the X-ray community about how to design and build a mission like this. We have technologies that are already quite mature due to a history of funding at various NASA centers and universities throughout the US. These are cutting-edge breakthrough technologies that we can put on a spacecraft with a lot of heritage that we would know how to start building, and that are going to give us these tremendous leaps in science capability. The three main areas that we identified, and I'll tell you a little bit about our process in just a bit, but the three main science topics that I'm going to give you a flavor of are the dawn of black holes, so finding the seeds of the supermassive black holes back to redshifts of 10, looking at the drivers of galaxy formation and evolution, which really imprint themselves in the hot gas, which is primarily observable in X-rays, and also the energetic side of stellar evolution. And stellar astronomy, understanding the star formation through its life with its planetary systems to its death and beyond, has been one of the cornerstones of astronomy for all of astronomy, understanding how stars work. And this has become a necessarily multi-wavelength endeavor, as we have seen. There are some processes that are you're only going to be able to study them in one wavelength or another, and then you have to bring it all together to get a complete picture of stellar evolution. Just to give you a brief history, so this was a large mission concept study that was convened by NASA. Paul Hertz, the head of astrophysics, he had 4 teams formed to study these large mission concepts in different wave bands. And this was stemming from previous decadal reports and other reports that were defining what are going to be the key science themes moving forward, and it was characterizing early black holes and feedback, understanding the archaeology of nearby galaxies, and how they got to be the way that they are, what drove their formation and evolution. Characterizing, again, the first starlight spectroscopically, looking at cosmic dawn, and measuring dark energy and the history of cosmic growth. So these were some of the main science themes, and you'll see these reflected in the science case that we brought forward. Our team formed in 2016. This was the initial formation of the science and technology definition team. That's when I joined. It's a group of about 15 scientists and another 6 or 7 technologists to work on this concept. We spent several years thinking about, and this was a wonderful exercise with an amazingly talented group of people, thinking about what are not the science questions now, but what are going to be the science questions in the 2030s, after the Vera Rubin telescope, after JWST, after WFIRST have been around and answered the questions that we're all thinking about now. What's going to be left? And what is going to be needed to make significant progress on those? So we spent years coming up with key ideas and key programs that would be part of our science report. And then we used those and defined possible observatory programs, observing strategies to figure out what are the capabilities that we need to actually make progress on this. That said, we're not proposing something that has its science plan defined. We envision Lynx as an entirely community-driven observatory. All of the science that I talk about here and anything that comes up would be entirely geo-driven to adapt to and respond to whatever scientific discoveries happen between now and the mid-2030s. And now we're in the phase where we've turned in our final report, and as I told the fellow members of the STDT, I mean, we essentially wrote like another PhD thesis. I mean, really, we produced like over 1,000 pages of science justification, of technology roadmaps, of budget estimates, but we produced these wonderful documents, as did all of the other teams, the other 3 teams. If you read the science cases, they are inspiring. And so what we want to do now is we've done this great study, all the teams have done this great study, and we should let the community know about it. Because even some of us weren't aware of the types of things that an observatory like this could do with these capabilities. So it's been a big part of the last many years of my life. And I want to put that in a human perspective. when I joined the STDT, I had 1 child, and I now have 3. And the youngest one has been walking since about the time we turned in the final report, right? And so, you know, seeing these things go from an initial seed to, you know, development and gaining capabilities and doing and having these things that you never would have expected has been a very parallel track in my life over the past many years. So let me go ahead and tell you about the observatory, briefly go through some of the instruments, and then tell you about the awesome science that it can do. So if you've ever seen an image of Chandra, this might not look too unfamiliar to you. And again, it's because we're going to go with a spacecraft that has proven heritage, that there's no new inventions needed for the spacecraft. It's a design that has been tested and proven to be extremely dependable for our needs. The main components of the observatory is the mirror assembly. I'll talk a bit about that. And then we have 3 instruments. We have a workhorse imager, the high definition X-ray imager. We have an X-ray microcalorimeter. This is essentially like an X-ray IFU that is going to be absolutely amazing in what it's going to allow us to do. And we also have a set of X-ray gradings. And our baseline requirement on those is a resolving power of R of 5,000, but in the lab they've already achieved R of 10,000 already. So all of our technologies are in a good state. So let me tell you a little bit about where we are here. For the mirrors, we knew going into this was going to be one of the biggest things that we had to get right. We looked at a number of different technologies for the mirror. We had a many months-long trade study with dozens of scientists and technologists involved. And the technology that we put forward for our baseline mission was the silicon metashell optics. These are being worked on by Will Zhang and his team at Goddard. And a few things worth pointing out to show how far things have come just in the last few years. If this isn't an area that you keep up with, a lot has changed in the past 5 years. What's shown here are data showing the figure of the substrate, which is a measure of how smooth the substrate needs to be so that the mirrors can be as accurate as we need. And we're already getting smoothness figures that are better than the Chandra mirrors. So the idea behind Lynx is we're going to have exquisite angular resolution, sub-arcsecond angular resolution like Chandra, but whereas with Chandra it's really just on axis, this is going to be over the whole large field of view. And the mirror segments are going to be these pieces of silicon that are machined and assembled by Will Zhang and his team. He's done a series of tests. This is not even the most recent one. This is just the most recent slide that I have of his results. What he presented at the AAS is even a little bit better than this. So this is this is a mirror pair that's been mounted and tested at an X-ray facility. And you see this odd shape here. You would, of course, want something nice and round and point-like. But what is happening here is because they test them in a horizontal facility, there are gravity distortions in these mirrors that we understand. So this half-power diameter is already around an arcsecond, and that is dominated by gravity distortions, which are understood. And when you take those out, because we understand gravity, it's already got a sub-arcsecond half-power diameter for this mirror pair. Now, of course, that's for one mirror pair, and we're talking about a lot of things, but we're already at a really good place with the mirrors. Certainly much farther along than we thought we would be. So we have a very well-defined roadmap for how to get to the mirrors that are needed for Lynx. We know how to do this. One of the components of the mirrors, if you're not familiar with how X-ray optics work, it's not normal incidence like optical mirrors. It's grazing incidence. So you have 2 grazing incidence surfaces that are done, and we're going to build that up by having nested mirrors, much as is done on most X-ray satellites like XMM and Chandra and NuStar. And it's a highly parallelizable process because we're going to be doing this fairly similar type of manufacturing and assembly for these structures over and over again. So Each module has about 60 segments. There's 611 of these modules with these segments. Those modules are going to be formed into these meta shells, and there are 12 nearly identical meta shells. And then the meta shells are going to be nested like this and fit together in the final mirror assembly. So it is a lot of surface for that grazing incidence optics, and we will get on the order of I just forgot the number. It's 5 or 7 thousand square centimeters of collecting area with these mirrors. And again, this is something that Will Zhang and his team have been doing for a long time. They have proven the quality of these mirror segments. The way that we envision constructing this mirror module lends itself to being mass producible, to using commercial off-the-shelf equipment. We don't have to invent the machines to make these. We're using silicon, which is a commodity because of its use in the semiconductor industry. So this is a very efficient, very cost-effective way to get us the sensitivity that we need with the angular resolution required to do the science that we want to accomplish. And again, the takeaway of the mirrors, as well as all the science instruments, is this is something that we know how to do. We have very well-defined roadmaps and have already gotten to places where we didn't think we'd be yet. So that's the mirrors. When things get to the focal plane, as I said, the workhorse camera that we're going to have is a Cmos-based X-ray imager. There are 3 viable technologies for this. This is probably the most mature of the technologies in our design. And not much to say here other than extremely low noise detectors that will have very small pixel sizes, well matched to the angular resolution of the telescope, and again, a number of technologies to get us there. And so what we're envisioning is an array of these about 22 arc minutes across, and the reason that we have them broken up like this is so that we can tilt them slightly to match the curved focal plane and maintain that exquisite angular resolution across the array. The most transformational instrument on here is the X-ray microcalorimeter. So this is going to be, if you are familiar with microcalorimeter technology that flew on ASTRO H, that is even being proposed for Athena. I'll talk about Athena a little bit, another X-ray mission. This microcalorimeter is much more capable than either of those. It's going to be a huge leap forward in terms of sensitivity and resolution. To accomplish all of the requirements that we had for this instrument, we actually have designed it in such a way that there are 3 different arrays. There's a main array of microcalorimeter pixels that's about 5 arc minutes across, and these pixels are going to be about an arc-second across. It'll have an energy resolution of 3 eV. So this is, again, this is like our IFU. That'll have a R of 2000 at about 6 keV. In the center of that main array, we have an enhanced main array. And the reason for this is to have smaller pixels with about the same, slightly better energy resolution, but really just smaller pixels so that we can take advantage of that sharp angular resolution at the centers of things where typically the structure is the smallest and we're going to resolve things the best. And then off to the side, we wanted something with even better energy resolution, but it would be hard to do that across the entire array. So off to the side, we have an ultra high resolution, and this resolution here is talking about energy resolution, which is going to have an energy resolution of 0.3 eV. So at the low energies, where it's hard to get that really good resolving power, we're going to have an R of 2000 at 0.6 keV. This is a an amazing device, a technological achievement. We're talking about nearly 100,000 pixels that need to be read out. The sensors need to be read out, and we've made great gains in all of this. If you were at the AAS and happened to stop by the Lynx booth, we actually had examples of all of the hardware. We had that mirror pair that I showed you a picture of. We had a 50,000 pixel array, microcalorimeter array, that's already been made, that meets our energy requirements. The main challenge in this is fabricating this array with the wire density necessary to read out all of these pixels. And that challenge has been overcome by Simon Bandler and his team with the use of superconducting wire buried beneath the surface. And in addition, instead of reading out all 100,000 pixels, or having 100,000 readouts, one for every pixel like you would normally do, we're going to use thermal multiplexing to reduce the number of sensor readouts to only about 4,000 needed for the main array. And that's about the number of sensors for the Athena microcalorimeter. So again, this is a technology that we know how to accomplish. And it does meet all of our energy resolution requirements. Finally, we have the X-ray gratings, and this will give us the highest resolving power. As I said, our requirement is an R of 5,000, but in the lab we've already seen results that show an R of 10,000. And we have two viable technologies for this. The off-plane gratings and the transmission gratings shown up here by the groups at MIT and at Penn State. And with the gratings, we're getting effective areas of 4,000 square centimeters at oxygen 7. So this is just a hugely, orders of magnitude leap over what we have currently with Chandra. Chandra still has the best X-ray gratings that have ever flown. And the Athena mission is not going to have gratings. It's not going to have that higher spectral resolution. So it won't be until we get something like Lynx that we are going to make these big gains. With this resolution, that's an order of magnitude better than Chandra, with an effective area that is way beyond what Chandra has, orders of magnitude beyond what Chandra has. Before I get to the science, I did want to talk just briefly about the cost, because this is something that everybody should be aware of, right? We did these mission concept studies, not for us, but for the community, right? This is something the community really should know about. And I thought it was important for us to go tell the community about Lynx, and I really hope that you have talks from the other mission concepts as well, so that you can be informed about the science that they're doing. And it's also important to consider the cost. We did our cost estimates in about 5 different ways. And they all converge to within a few percent at the 40% confidence level. So obviously any cost has a confidence level associated with it. You learn about these S-curves when you do this type of thing. It's like, well, this cost, you think you can achieve that with this much confidence. And so at the 40 to 70% confidence interval, we're between 4.8 and 6.2 billion. As is indicated there, at the low end, things were within 5% of each other. These 5 different, very different cost estimates that were used, independently done by a group at Marshall, by doing heritage, grassroots accounting based on Chandra, having aerospace do an independent cost analysis for us, and they all came in about the same. And this cost includes the Paul Hertz mandated $350 million for launch and $400 million for operations. That's basically something all of the mission concepts had to deal with. This does not include potential foreign contributions. But we have talked with the space agencies in Italy, in Germany, in the Netherlands, about ways that they could make contributions to Lynx, that would actually reduce cost. Whenever you bring something in from Europe or from Japan, the cost savings can easily be eaten up by additional integration, by just different ideas about how things should be done. And so we have actually identified a number of ways that the Europeans could contribute, and they are interested in doing this. They've said that they are interested in contributing, and they could do it in a way that would actually reduce cost. So, the takeaway from the capabilities of the mission and what we propose to do, I think this slide represents it best. Lynx is going to give us high angular resolution, not just at the center on axis like Chandra does. So these are representing Chandra's 4 mirrors, and this is a Chandra deep field. And you can see how the point spread function grows as you get off axis. These sources appear to get bigger. With Lynx, we maintain that sub-arcsecond point spread function across the entire 22 arc-minute field of view. And we also have a sensitivity that is over an order of magnitude greater. So that is going to give us the ability to survey parts of the sky that is 1,000 times faster, 1,000 times greater than Chandra's ability to do surveys. And I'll put that in perspective in just a second. Because this is really going to be transformational. And we tried to think about how can we describe how transformational are these capabilities going to be. So we know that astronomy has been undergoing a revolution thanks to IFUs, right? The ability to have spectra from every part of the sky when you look at a certain region has just transformed our way of thinking about and understanding galaxies. The equivalent for Lynx, if you think about the path that optical astronomy has taken from the first astrophotographs to state-of-the-art imaging that is still done with the Hubble Space Telescope now, to going beyond imaging, to having something like the MUSE IFU on an 8-meter VLT. We're seeing a similar type of trajectory in the X-rays, from the first imaging X-ray satellite Einstein to now what we have with Chandra, where we do have data cubes of limited resolution. With the Lynx microcalorimeter and the mirrors on Lynx, the jump from Chandra to Lynx would be equivalent to going from a 1-meter telescope with the 1980s era CCD to the MUSE spectrograph on VLT, right? And this is what you should expect from any type of flagship mission concept. It's those orders of magnitude gains in capabilities. That's what's going to unlock new physics, new discoveries, and allow it to do things that we haven't even thought of. I want to tell you about the things that we've thought it can do and will be able to do. But you have to understand that when you make that kind of leap from a 1-meter telescope with a CCD to 8-meter telescope with MUSE, you're just in a whole different ballgame. So let me briefly talk about our science pillars that help drive and define our requirements. The first was the dawn of black holes. Excuse me. So we know that supermassive black holes were in place very early in the universe, but we don't know where they came from. We don't know what were the seeds of these supermassive black holes. Were they light or were they heavy, is the basic question. Was it a direct collapse? Was it mergers and accretion? Was it some combination of the two? So that's the major question, right? One of the major questions in astronomy is how did we get these supermassive black holes? And so looking at the dawn of black holes, as I said, drives a lot of our observatory requirements for point spread function, for sensitivity, and for field of view. So illustrated here are a few different models in very cartoon form about how you can get to the observed quasars at redshift of 7 or 8 through a variety of different routes. And the problem with black holes not having any hair is when you observe them here, you're already past the point of knowing how they got to be there. That information has already been erased. So to actually get to a point where you can distinguish between different models, different formation scenarios, or how much of one contributed versus how much of the other one contributed. What we define is that you have to get down to redshifts of about 10 or earlier. And that's what Lynx has been designed to do, to detect 10,000 solar mass black holes at a redshift of 10, right? And that is going to provide the direct observational input needed to determine the origin of the supermassive black holes, to determine what the seeds were. Here is an example of a simulated Lynx deep field, where you can see all of the X-ray sources indicated. So JWST is going to find the first galaxies in the universe, but it's not going to really know much about their black holes. For that, you're going to need Lynx. So Lynx is going to tell you where the black holes are and be able to associate them with individual galaxies, and that's something that requires the type of angular resolution that the European mission Athena won't have. Okay, so I was going to move on to our next science pillar, but I'm happy to take questions along the way, or we can save them all to the end. As I said, I'm trying to cover a lot because I want to give you a flavor of the science that Lynx can do, so it's hard to go too in-depth in any one thing. So it's kind of a broad overview or a quick survey of what Lynx can do.
I've got a quick question.
Sure.
So on this last point, if you're probing beyond redshift 10, I guess the rest wavelengths of the X-rays are studying, what, 100 kilovolts, something like that? Or are there issues with that, because the spectrum, I guess, is probably pretty steep?
Correct. So what we have done is we have used new star observations of nearby galaxies to give us a handle on the different spectra seen from X-ray binaries and from the supermassive black holes, right? Because certainly in here, the difference between the teal and magenta points are X-ray binaries versus supermassive black holes. So with the new star observations of the nearby universe, we have an observational handle on what those different spectra look like.
So I've forgotten the hardness properties of different populations of sources. What does that favor, sort of, by going to really harder X-rays as you move forward?
I mean, unless we're looking at a blazar, the X-ray binaries are going to be harder.
Okay.
Yes?
This is probably a naive question, but so you were just showing the just approved everything Lynx compared to Athena. I know that Athena's a European-based thing, but if Europeans are interested in joining the Lynx, what's the point of making Athena?
Well, I'm not going to get into European Space Agency politics, but that was picked by things similar to the Decadal Survey in Europe as the M1, L2, thank you. I forget their designations as well, as the concept that goes forward. Here's the thing to understand about Athena. Basically, Athena is a mission. They said, okay, you have about €1 billion and build the best thing you can. I'm oversimplifying terribly, but in the interest of time. That would be equivalent to this new thing that NASA is looking at, which is a probe class mission. It's about $1 billion mission. So there's amazing things that you can do with that. And I'll compare and contrast Athena and Lynx in a little bit. And they're very orthogonal missions. It's kind of like, if you have Arecibo, why do you need the VLA? Well, yes, they both are radio observatories, but they're doing very different types of observations. Okay, well, I'll move on and talk about galaxy formation and evolution. This is fascinating science. This is one of the areas that I learned the most about being part of this SDDT. I mean, it's not my science, but I was just really impressed with what Lynx will be able to do in this area. As one of our members put it, Piero Medal said that Lynx would just finish the textbook on galaxy formation and evolution. It would provide the answers that people have been wanting for a long time. One of the ways to see that, and I'll show a few other ways as well, but I think for me, one of the most visually striking ways to see this are the results of these two simulations that are showing what's happening with the density and temperature of the gas, where the metals are, and where you form stars and the type of galaxies that you get. And if you focus on this rightmost panel, you might have a hard time seeing the differences between the galaxies that you get in these two different simulations. But what's different about these two simulations is only their input physics of feedback, right? So feedback, we know now, is a crucial component in shaping galaxies and giving us the galaxies that we see, but we have a lot of questions. And you can do very different input physics for your feedback, get star light that looks essentially identical. But it's in the higher temperature gas, which you're going to see best in the X-rays. Like once you get above a halo mass of about 10 to the 12 solar masses, the gas that you get is beyond the UV ionization states, so you don't see it in the UV. You're going to see it in the X-rays. So this is why we say most of the baryons in the universe, for most of cosmic time, are going to be observable in X-rays. Observing images like this is going to give us the clearest line into understanding what feedback processes are and are not important. So the processes that define the state of that gas are the same ones that regulate the growth and create the diversity of galaxy morphologies. And Lynx is really designed to test them all. It's going to characterize the hot gas in the galactic halos, not just in emission, seeing it directly, but also in absorption. And this has been driving a lot of our throughput requirements and spectral resolving power to detect these very weak emission lines from multiple ion species and to characterize the kinematic structure of the CGM, of the circumgalactic gas. And so that, again, what I wanted to hit on is that feedback comes in a lot of flavors and modes. And Lynx is really designed to get at all of them. Here is an example of a simulation that was done on an M82-like galaxy, where observed with Lynx's microcalorimeter, which will have that resolving power at the low energies where these ions reside, to be able to give us velocity differences of 100 kilometers per second to tell us about the flows that are happening from the starburst process. And it's really, as I said, it's almost designed for this problem of galaxy feedback, of galaxy formation and evolution, and really observing feedback in all of its glory, in all of its forms. Okay, moving along quickly. Again, I can't spend too much time on any one thing, but the last science pillar that I want to talk about is the energetic side of stellar evolution. So we have entered with both feet the era of multi-messenger astronomy with the LIGO detections of merging neutron stars. And we're also in an era when studies of exoplanets are moving toward holistic assessments of habitability conditions. And so we need data across the spectrum to understand galaxies and to understand the cosmic cycle of elements. What we can do in X-rays, studying, I'm going to highlight two aspects in particular, which is at the birth of stars and the death of stars. When stars form, in particular the M dwarfs that are the subject of a lot of interest, these are active stars, they have a lot of X-ray flares, and in fact, X-rays from the young M dwarfs are one of the best indicators of a young stellar object. You have the infrared excess, but those disks dissipate in a few million years, whereas they can remain X-ray active, magnetically active for tens of millions of years, 70 million years or so. And so for quite a much longer range, the X-rays are really going to give you the best handle on that young stellar population. Of course, it's the X-ray and the infrared together that give you the most complete picture. Now, Chandra, in its studies of nearby or of young star-forming regions, it really is limited to the most nearby. Chandra can only detect the full mass spectrum of stars only out to about 400 parsecs out to Orion, and that's it. And for spectroscopy with the gradings, it's even closer than that. It's really only the nearest stars that Chandra can give us good data on. Lynx's sensitivity is going to extend that horizon to be able to detect the full mass spectrum of young stars out to 5 kiloparsecs, over an order of magnitude increase in the distance out to which we can observe, getting us to these much richer star-forming regions in the spiral arms. This is an example of the type of stellar spectrum that Lynx would obtain from a star in one of these star-forming regions. And for comparison, this is the quality of data that you get with Chandra. Again, Chandra gradings are still the most, have the most resolving power of any X-ray instrument to date. This is what the data would look like with Athena's microcalorimeter, because again, Athena doesn't have gradings. And with Lynx, we see this rich variety of lines that will tell us about what's happening on the stellar surface, about how those connection events are occurring. Can even tell us about binarity of the stars. We'll be able to resolve the lines as a function of orbital period because of that spectral resolution. So again, it's just going to open up this world of stellar astrophysics out to a much greater region of the sky. To illustrate the gains that we'll have at the other end of a star's life in studying supernova remnants, I thought this might be a good place to just show you an example of the different types of data cubes that you would get studying a supernova with Chandra and its CCD energy resolution versus studying it with a supernova remnant with Lynx and its microcalorimeter resolution. The richness of the data cube itself is proxy for the amazing richness of physics that we'll be able to uncover for supernova remnants in our galaxy. For me, the most exciting side of this is actually in studies of local group galaxies with Lynx. This image here shows a lot of Chandra-detected supernova remnants in M33. Chandra can make a detection, with as few as 10 counts, but you don't get much of a spectrum out of that. With Lynx, we will get this quality spectra from every object in an image like this. And we will be able to type directly from the Lynx data whether that was a remnant of a type 1 or a type 2 supernova. And we'll be able to do this for all of the galaxies of the local group and beyond, out to 5 to 10 megaparsecs. So this is really going to move supernova remnant studies into the era like population studies, and getting a much better understanding of how the local conditions in the galaxy lead to different types of outcomes for the various stars, what type of supernovae they produce. Okay, I said I would, so that was what I wanted to do on the pillars science that we talked about, these 3 pillars that we identified. It has come up, and so I did want to compare and contrast Chandra, which is a satellite you might be familiar with, and Lynx and Athena. And we've done it on this spider plot, the spider diagram, that each axis out from the center is a different capability that your observatory would have. They've been normalized to Chandra. So Chandra has a value of 1, and each ring going out is another order of magnitude beyond that. And you can see that Lynx's main advantages are in the effective area for the gradings, for the energy resolution for imaging, for the sensitivity, for having a field of view with sub-arcsecond resolution. We're talking about orders of magnitude gain along all of these axes. If we look at where Athena would fit on a diagram like this, so Athena is in this dark red here, you can see that by and large the capabilities are orthogonal. And the missions are really designed to do 2 different things. Athena is going to be the first satellite to fly a microcalorimeter with more than a handful of pixels, and it's absolutely going to have amazing results and teach us new things. But it is not going to accomplish the kind of science that needs really high sensitivity with really fine angular resolution and a really high resolving power. So if you read anything about Athena, you'll see that their science case is built on understanding the hot and energetic universe of doing large surveys and following transients like gamma ray bursts. And our science was really driven by these three pillars that I gave you just the tip of the iceberg on, but that's what drove our requirements, and it is very, as I said, orthogonal, very complementary to what Athena will be doing. How much time do I have? Am I aiming for Okay. So those pillars drove our requirements. But as I said, it's not like we envision this as, this is definitely what the observatory is going to do. Lynx is envisioned to be entirely geo-driven, so that whatever happens between now and the mid-2030s, it can respond to, everything can be competed, and the best ideas will get time, as is the goal now. So I wanted to talk about just a couple things that we thought were cool and important, and things that Lynx can do, if not being the only facility that could do it, doing it better and in a clearer way than other facilities, that we would see as a large part of the observatory science. The mission was designed so that to accomplish our three pillars would take about half of the time of a nominal 5-year mission. That said, Lynx has been designed for longevity. It could easily go 20 years. It has no showstoppers that would keep it from going decades. And that science that I just told you about would fit within half of the primary 5-year mission. So there's a lot of room for other ideas, a lot of room for other discoveries. One of the most interesting, in my opinion, now this is getting very selective, one of the most interesting things that Lynx would be able to do would be to follow up on the chirp signals of merging supermassive black holes by LISA. LISA should be able to detect these with several days, if not weeks, of lead time before the merger. And it'll give us a rough location in the sky. And you can go and you can point a sensitive X-ray telescope in there. You might have to search around a little bit, but you have a periodicity that you know to search for. So you have a signal that you know what it looks like. And so Lynx will be able to find these merging supermassive black holes before the merger, because LISA will give the heads up of days to weeks. And so to be able to follow that electromagnetically and gravitational wave, I mean, that's just, I was stunned. I couldn't believe this was something that would be possible, and yet it is. And this is, yeah, this is some wonderful work that was done by Zoltan Hyman, showing what you could do with that lead time that LISA is going to give you. There is a really interesting aspect of the epoch of reionization that Lynx will contribute in a very meaningful way to. And it has to do with how much heating is being done by the X-ray binaries early in the universe. And the main science that would come here would be in cross-correlating the 21 centimeter signals with the Lynx detected sources and backgrounds, and understanding what was going on before the epoch of reionization to actually heat the universe back up, whether that was what we typically assume from X-ray binaries, or there are some indications that X-ray binaries might actually be a bit more significant of a contribution. Okay, finally, my last example of science, and I'll spend a few minutes on this because it's close to my heart, is Lynx being used to study the stellar IMF and the stellar mass to light ratio, which is something you would never typically associate with an X-ray telescope, but it's actually something that we've done with Chandra to get at the stellar IMF. And the motivation for this is best stated in a nice quote by Carlos Frank, which I'll go ahead and read it because he puts it very bluntly. Nobody ever measures the stellar mass. It's not a measurable thing. It's an inferred quantity. You measure light. You can measure light in many bands, but you infer stellar mass. Everybody seems to agree on certain assumptions that are completely unproven.
To be fair, Darren voice says
Okay. Yes.
Yes.
Yes. So I mean, this is well known, right? And for those of you not in this field, I want to give you a sense of it. So this was a paper put out a couple of years ago that looked at the initial mass function that you would infer by studying galaxies and trying to determine it from strong lensing, from stellar dynamics, and from population synthesis studies. And each method has uncertainty associated with it. For the lensing and the stellar dynamics, it's basically what you assume about the dark matter that you get from simulations. And that's what you have to put in. And from stellar population synthesis, you are subject to very large uncertainties depending on what you assume about the low mass cutoff of the IMF. And to illustrate how severe an uncertainty this is, another paper around the same time by some of the same authors, forgive me, but I am going to quote directly from this paper. To illustrate the sensitivity of the total mass to the cutoff for a single power law, 2.7, the mass to light ratio is 70% higher if the cutoff is 0.05 solar masses compared to 0.08 solar masses, right? So a small change in where you decide to cut off the IMF gives you almost a factor of 2 difference in your mass estimate for that galaxy. Okay, so how do we get around this? Well, we use a technique that is not subject to these uncertainties, that isn't subject to these assumptions, and it has to do with the microlensing of quadruply lensed quasars. So if you look, and until recently we knew of maybe 12.5 of these. We actually know of several more now in recent large surveys. When you look at these in the optical, you see the 4 images of the quasar, the lensing galaxy right there. If you compare it to a model, which is over-constrained, that's why we like the ones with 4 images, because we get a lot of constraints in the mass model of the lensing galaxy. And so we know the mass model very well, and there's often, and this has been seen in the optical for decades, there's an anomaly with one of the images that it's fainter than it should be. It should be the brightest, and it isn't. And the explanation for that was that further lensing was happening either by dark matter subhalos or by stars. And so that was called millilensing and microlensing. So along comes Chandra in the 2000s, able to resolve these systems. The separations here are on the order of an arcsecond or less. So you really need something with Chandra's resolution to do this. And we saw that, yes, this was anomalous in the optical. It should have been the brightest, and it wasn't. In the X-rays, it's actually even worse. The problem is even worse. And the explanation for this is that it's not dark matter subhalos. Those would have given you the same effect for the optical and the X-rays. And it has to do with the size of that perturbing mass's Einstein radius compared to the size of the emission region of the quasar, of the disk. For dark matter subhalos, that Einstein radius would be much larger than either optical or X-rays, whereas for stars, it's much larger than X-rays, you get a bigger effect. But it's sort of comparable to the optical emitting regions, so that effect is washed out. So Chandra observations really indicated that this was due to microlensing by the stars. And so that allowed us to use microlensing as a tool to study both the quasars, the emission disk of the quasar, the accretion disk of the quasar, and the lensing galaxies. The thing to understand is that that probability of having that strong effect, like I showed you, is a non-monotonic function of the stellar density, right? From the large-scale lensing, we know how much mass is there. Is it in stars or is it in smooth dark matter? We don't know. And depending on what you assume about what percentage of that is in stars, you get very different probabilities for having a strong demagnification. So this is magnification on the x-axis. 1 means you have no effects. And so that strong demagnification, like we saw, is not very prominent for low stellar masses or high stellar fractions, but somewhere in the middle is where it peaks. And so we can use this and do a Bayesian analysis and figure out what is the most likely stellar fraction. We did that for the ensemble of quads. It was about a dozen known at the time. And going through that Lynx galaxy at an impact parameter about 7 kiloparsecs, the most likely stellar fraction was about 7%. Okay, so we know the overall mass. We now know how much of that mass is in stars. And it's because this technique is sensitive to the graininess of the gravitational potential, right? Whether that's stars or brown dwarfs or neutron stars or things that are invisible in the optical. It's sensitive to that graininess. So we know how much mass is in stellar things. We also know how much light is there. So we can actually determine the stellar mass to light function through these observations, through X-ray observations and the corresponding optical observations of the Lynx galaxies. We characterize that as a correction factor to the fundamental plane. It turned out to be the most straightforward way to do that, whereas you say what mass are you going to get if you just assume a saltpeter IMF, and then you can correct that by this factor that we determined, which turned out to be about a 30% correction, but it was uncertain because of the small size of the sample. This was only about 13 quads that we knew of at the time, but this is how you would do that. So you would be able to, for this ensemble, determine the mass to light ratio as this correction factor for the fundamental plane. So, certainly when Chandra was launched, nobody was making the case for Chandra based on stellar mass to light ratios, which is a fundamental astronomical measurement, but it's something that Chandra was able to do. And it's an example, I think, of the types of things that are going to happen when you make these transformational leaps in capability. You're going to get to do things that nobody would have ever thought would be possible. Where does Lynx come into play? Well, we know that the Vera Rubin telescope is going to just be an absolute bonanza for many areas of astronomy, in particular for finding and studying a lot of the quadruply lensed quasars. The full power is really only unlocked with these high resolution, high spatial resolution X-ray observations, because that's what gives you the cleanest signal of the microlens. So Lynx would be able to follow up promising subsets of these newly discovered lensed quasars. Here is a distribution as a function of Lynx redshift. So this is the Lynx galaxy redshift. So there will be, as I said, just a bonanza of quads. And we can imagine doing the type of analysis that I just showed you actually as a function of Lynx galaxy redshift, determining the mass to light ratio and the IMF as a function of redshift. So I think a pretty cool example of observatory science that we can do with Lynx. So Lynx is going to give us critical advances in the areas that I mentioned. It's going to have a major impact across the astrophysical landscape. And if nothing else, one of the messages that I wanted to impart today is that this is not an X-ray observatory for X-ray astronomers. This is a flagship NASA mission. This really is an observatory for everybody, right? Just like in a few years, we're all going to be JWST astronomers, right? We're all going to be something astronomers in the 2030s, depending on what happens. And we have tried to design and make a science case that shows how this mission would address fundamental questions in all of astrophysics. And when I think about who's really going to be using it, I I don't think so much about myself, but I think about this guy right here. This is my son Henry, with an artist representation of a lynx that he gave me once. He drew it for me. He said, Daddy, I drew you a lynx because I know how much you like lynxes because you talk about them all the time. Which makes it impossible for me not to show this picture. But also because it's been an incredible pleasure for me to be part of this team for this many years. And to think about something that wouldn't even launch until the earliest of the mid-2030s. It's been this great exercise and endeavor in long-term thinking and thinking about broad themes and areas, which, you know, for someone like me where the Hubble deadline almost catches me by surprise every year, to go through this and to think about these things like, no, beyond JWST, beyond W1st, what are gonna be the big questions still? Like, and thinking about making something for the next generations of astronomers has been incredibly meaningful. So thank you for giving me the time to share that with you, and I'm happy to answer any questions now, at lunch, throughout the day. So thanks a lot.